This is the second video for lesson 8.3. We're starting with example 5. Up till now we've looked at exponential growth examples. Now we're going to look at exponential decay examples. So here we have a snowmobile. A new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. So we know it's decay because it's decreasing. 10% is going to be our R value, but then convert it to a decimal. Okay, so write an exponential decay model giving the snowmobile's value, y, in dollars after t years. Then we're going to estimate and graph. So y is the value. We know the general form for decay is a times 1 minus r to the x. So here, a is our initial value, that's 4,200 or 4,200, and then we have 1 minus our value, so 0.1, to the x, that's time, and here it tells us to use t, so t for time. So simplifying, we get 4,200 times 0.9 to the t power. So that is our exponential decay model. Now it asks us to graph the model. You would want to use your graphing calculator for this. You'd want to enter this equation in your calculator. So you should go ahead and put that in for y1. So instead of y, it would be y1 in your calculator. All right, now that you've done that, you should go to the table. I've already written in a table for us. So this should match the one on your calculator. So put in values for 0, 1, 2, 3, 4, 5, and 10. Now we're going to want to graph this, do a rough graph. We want to label our axes. So we know on the x-axis we have time in years, because looking at the original problem, it's decreasing each year. Then the y-axis is the value in dollars of the snowmobile. All right, let's plot, well actually let's determine what each of these tick marks should be. It's good to get a decent view of what's happening, so I'm going to go from 0 to 10. So each of these tick marks is going to be 2 years. Now you could choose other values, but I think that'll work pretty well. Y values, we need to go all the way up to 4,200 and down towards 0. So if I divide 4,200 by 10, I get 420. 420 isn't a very nice number. Let's round up to 500. So let's make this 500. This would be 1,000, 1,500, 2,000, 3,000, 4,000. So my graph should go up to about 4,500. Now we're ready to start plotting points. So 4,200 for 0. For 1 year, I want 3,000, about 3,800. So it's going to be about there. Year 2 is 3,400. So here. Year 3, about 3,100. 4, 2,700, 5, about 2,500. I'm going to go all the way out to year 10. That's about 1,500, so it goes all the way down to here. I know that this is exponential, so it should curve. And we could take this graph out even further if we wanted to see it approaching 0 more closely. But that's pretty good for a rough graph. Then the problem asked us to estimate the value, estimate when the value of the snowmobile will be $2,500. So looking at our graph here, 2,500. So it looks like it'll be about 4 years, but we want to have a more exact value than that. So you have the equation for this graph in y1, and y2, we want to put 2,500. That will graph this line, and then we can find the intersection. So take a second to plug in 2500 and then find the intersection. All right, now that you found the intersection on your calculator, you should have about 4.9, 2500. Okay, so it'll be about $2,500 after 4.9 years. So I'm going to go back here to answer this question. So about 4.9 years, or you could say 5 years later. All right, let's take a look at an extension question. What would our equation be if the snowmobile's value decreased by 10% every 3 years? So we don't want it to happen every year. We want it to happen to every 3 years. So we want to slow this process down. So thinking about our original equation, which part controls how fast things are changing? Well, it's your time. So if we want to slow this down by 1/3, we're going to change the equation so that it is 4,200 times 0.9 to, you could do the 1/3 t, or t divide by 3. That's going to change the table and change the rate at which things are changing to slow it down. So this change only happens every 3 years. Okay, so let's modify the exponential equation formula that I gave you guys before. So before we had y equals a times 1 minus r to the x. Here I'm going to change it to t for time, and then I'm going to have n as the amount of time needed for your quantity to decrease by r. So basically I'm adding in this value. That's going to tell you how often you're having your decrease, after how many units of time. So we're going to practice looking for n values, or how often something is decreasing, in a little bit. But first, let's practice just coming up with exponential decay equations. So you should try this problem on your own. Pause the video, and then once you've tried it on your own, come back and check your work here. Okay, so assuming you've solved this problem, your equation should be y equals 128, because that's our initial value. Half the players are eliminated each time, so we have a decrease of 50%. So 1 minus 0.5 will give us 0.5 to the t, or to the x. So x here, in this case, x is the number of rounds. That's essentially our unit of time. Okay, you could also represent this as a 1/2 instead of a 0.5. So your table should look like this. So the question was, how many players remain after 5 rounds? Well, 4 players remain after 5 rounds. And if we were to look at that on a graph, it would look like this. And since you could do this on your calculator, you could find the value of the number of players by going to second trace, doing option number 1, which is the value option, and typing in x equals 5. And it would tell you that y equals 4. Okay, on to special cases of exponential decay. So I think this is a really interesting application of what we're doing, and it's all about chemistry. Radioactive decay is the process by which an unstable atom of a certain kind of element, so it could be carbon or oxygen or potassium, something like that, changes by giving off radiation or energy in the form of waves or particles. So you have an unstable atom, it doesn't stay what it normally is. It's changing and giving off energy as it changes. So this can happen in various ways, but it usually, or almost always, changes the nucleus of the atom. That means that the atom's mass changes, and then it may actually become a different kind of element. So we know elements are determined by the number of protons. If the nucleus loses a proton, it's not going to stay that element anymore. It's going to become something else. There are 29 naturally occurring elements on Earth that are radioactive, so that they decay and can become other kinds of atoms. Two examples are carbon-14 and uranium. Uranium has a bunch of different kinds of atoms that can decay. So carbon-14 is all around us, just like carbon-12. Carbon-12 is the normal version of carbon. Carbon-14 is the radioactive one. And it mixes with regular carbon-12 at a specific ratio. So there's a small number of carbon-14s compared to carbon-12s. And when a plant or animal dies, it stops taking in carbon. So it stops taking in any kind of carbon, including carbon-14. But because carbon-14 is radioactive, it will break down over time. So even though this plant, so let's say you have a tree, let's say the tree has died, the regular carbon stays put, but the carbon-14 changes. It breaks down over time. So there will be less and less of it in the dead tree, or the dead plant, or dead animal. Half of all carbon-14s will have changed within 5,730 years. We call that time frame the half-life of carbon-14. So half-life is the amount of time it takes for 50% of something to degrade or change, something radioactive to change. Archaeologists measure the amount of carbon-14 in wood and dead animals, and based on that, they can figure out how long that piece of wood or animal Sorry, I said that sentence wrong. They can figure out how long ago that wood was part of a piece of plant or that animal was a living organism. The process of figuring out how long ago that thing existed is called carbon dating. So here's another example of that. Uranium is a heavy metal that was formed in supernovas about 6.6 billion years ago. While it's not common in the solar system, today its slow radioactive decay provides the main source of heat inside Earth. So there are uraniums inside the Earth, and they give off heat as they degrade and become other kinds of uranium. And when they give off heat, they cause convection and continental drift. So it's kind of cool to think about all of the effects of radioactivity. So here's some examples of radioactive materials. We call the radioactive materials isotopes. So they're different kinds of elements. So there's nickel, 63. 63 is not the normal number of protons in nickel, but if it has 63, it will be radioactive. We have curium 246, calcium 41, uranium 235, and thulium 171. So I've set up exponential decay equations for these. So the amount of nickel here depends on the initial amount you have, and then the ratio is 1/2, because 50% of it is lost over time. And T would normally be in years, but it's not losing half of its mass in 1 year. It loses its mass, half of its mass, every 100.1 years. So these are examples of the N value that I talked about on our previous page. So when we go back to here, the amount of time needed for your quantity to decrease by half or by whatever R is, we can see how often it's decreasing by half looking at that value. So when we look at curium, we can tell curium's half-life, or the amount of time it takes to lose half of it, is 4,730 years. So these elements have really long half-lives. Here for calcium, it is 103,000 years. Uranium, that's a lot of zeros. Let's see, 1, 2. Okay, so this looks like it's 4 billion years. We could change this to 4.468 times 10 to the 9th years. So we're talking 4 billion years for uranium. All right, thulium has a really short half-life, 1.92 years. So it just depends on the element and the isotope what its half-life is. Okay, so let's do some practice problems using that information or those kinds of equations. Iodine 131 is used to destroy thyroid tissue in the treatment of an overactive thyroid. So this is true. This is a medical application of exponential decay. The half-life of iodine 131 is 8 days. If a hospital receives a shipment of 200 grams of iodine 131, how much I-131 would remain after 32 days? Okay, so we've got all the key pieces of information. Let's start marking what all these values are. So 200 grams, that's our initial value. We know in our equation that that is the A value. The half-life is 8 days, so you can think of that as your N value. And it's asking about 32 days, so that's the amount of time. All right, let's start writing an equation. We know the amount of iodine, I, we're going to write our general equation, equals our initial amount, which is 200, times 1/2, because this is half-life, or you could think of 1 minus 50%. 100 minus 50% would be 50, so as a decimal, that's 0.5 or 1/2. And then it would be T divided by the half-life, which was 8 days. Okay, so note here, T definitely has to be in days. That's our unit of time. And it asks us specifically to find how much would be left after 32 days. So I'm going to take out T, and I'm going to put in 32. Okay, so plug that into your calculator, and you get 12.5 units grams. So grams of iodine, or of I-131. All right, next it's your turn to try B and C. Once you've tried them, check back in on this video. Okay, so in B, your general equation should have been technetium equals 200 times 1/2 to the T divided by 6. Here, T is in hours. So the question was, how much remains after 24 hours? I used function notation here to show that I'm plugging in 24, and I plugged in 24 for T, and I got 12.5 grams. So even though the half-life was different, because the initial amount was the same, and the number of half-lives is the same, so 32 days meant that we had time for 4 half-lives, and 24 hours meant we had enough time for 4 half-lives. We end up with the same result, 12.5 grams. All right, for part C, your equation should be M equals 32 times 1/2 to the T divided by 3. Plug in 15 days, and your result is 1 gram of mercury. Now notice I wrote it like this, but when I plugged it in my calculator, I actually typed it in like this. So I did the multiplication, I used a decimal, you can use the decimal or the fraction, and then I had a caret and I put 5. So I actually simplified this mentally and plugged in 5 instead of plugging in 15 divided by 3. If you don't simplify and you put in 15 divided by 3, you have to be really careful to make sure that you've got parentheses around 15 divided by 3 if you have an 83. If you have one of the newer models, your calculator probably knows that 15 divided by 3 is in the exponent. If you have an older model, you will need the parentheses around, around 15 divided by 3. Okay, on to more special cases, but this time special cases of exponential growth. So one of the most common applications of exponential growth is interest. Interest is when you put money in the bank and as you leave it there, the bank essentially gives you money for leaving it in the bank. They want your money in the bank, so they reward you by giving you interest. They base the interest as a percentage of how much you put in the bank. You guys may have learned about this in your econ class. So we're going to learn about compound interest and continuously compounded interest. So compound interest is interest paid on an initial investment, so on how much you put in originally, and that original investment is called the principal. and on whatever else you've earned in interest. So let's look at compound interest. Consider your initial principal or initial amount to be P. So P is the initial amount, or the principal. Then you have the equation 1 plus R over N. R is your rate of growth, just like we have been doing all along. And it's going to be expressed as a decimal. But compounding means that it's not happening every year necessarily. It could be happening twice a year, 3 times a year, 12 times a year, 365 times a year. The number of times per year it's compounded, or you earn interest on it, is n. So number of times compounded per year. And then instead of just having x, or just a t, we have the number of compounds times time. Now, this is a formula that you are going to have to memorize. You could be quizzed or tested on this on the SAT, and they won't give you the formula. You have to know it. You may also need this formula in other classes like calculus or a business math class. Okay, so if we are not just compounding daily, but we're compounding an infinite number of times per year, we call that continuous compound interest. Now, when we're compounding continuously, so at every moment, we have a different equation, and it involves the constant E. So A is the amount of money you will have after interest. P is still your principal. So P is still principal, or your initial amount. We know E is the constant. It is about 2.718. R is still the rate, and T is still time. So we're going to look at some examples of when you'll use these equations. And again, this is another equation that you just have to have memorized. So in example 7, you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. If the frequency is quarterly, that means that it's deposited 4 times a year. 1 quarter is 1/4, so think about 4 times a year. So here, the number of times it's compounded is 4. The initial amount, or the principal, is 4,000, given here. And the rate of interest is 2.92%. Now remember, we need to change that to a decimal for R. So that's 0.0292. And then it's asking for the balance after 1 year. So T is 1. So let's plug it into the formula for compound interest. So we're going to use this one. So A, or the amount in our bank account, is equal to the principal, so 4,000, times 1 plus R divided by N, which is 4, to the 4 times 1. So you can plug it into your calculator just like this, making sure that you use parentheses. And then here, either that you use parentheses or you simplify it. So we can just think 4 times 1 is 4. So we're just going to put 4. All right, when you plug that in, you should get 4,118. And then it's 0.085. 0.085 would round up to 9 at the end. Now we're rounding to 2 decimal places instead of the usual 3 because this is money and you only have cents, right? Like penny is 0.01, so we can't go past that. Okay, let's talk about compounding daily. If you're compounding daily, how many times are you compounding per year? 365. Our principal and our R value and T are all still the same, so we can just start plugging into the formula. So 4,000 times 1 plus 0.0292 divided by 365 times 365 times 4. Times 1, because we're multiplying by T, and our T value is 1 year. Okay, so, again, as a quick note, if this had been some value other than 1, let's say it was 2, if you were to enter it in the calculator, you'd want to make sure that you had parentheses around this, or that you actually multiplied this part out before you plugged it in the calculator. As it is, 365 times 1 is just 365, so that makes this pretty easy for us. All right, and when we plug that in, we get 4,118.52, and that's in dollars. Okay, so let's think about what this means. This means that if we put $4,000 in the bank and we're earning interest, and the interest is being compounded daily, you're going to have $4,118.52 in the bank. That means just for leaving your money in the bank, you've earned an extra $118.52. Now, in reality, often the amount of interest offered is lower than this, so you're not going to make that much money. But if you did, that would be pretty sweet, earning an extra $118 just for having it in the bank. And we can tell the difference between quarterly compounding and daily compounding. It makes a difference, but it doesn't make a huge difference here, or at least not with sums that are so small. Okay, next let's look at continuously compounding interest. So we have a different formula for that. The formula for that one is A equals P times E to the RT. All right, so our principal is still the same. It's 4,000. Then we have E, that's a 2.718, and then to your rate, so 0.0292 times the amount of time, in this case 1 year. And that comes out to be about 4,118.52 cents. So doesn't look like there's a difference here, but that's because we rounded. There was a slight difference between these two. Okay, so if you're unsure how to plug E in on your calculator, look for the LN button just above on. The E is above that LN button, so you can press second LN. That'll generate this E for you when you plug it in the calculator. And please make sure you're actually trying these as we do them so that you know you can do it correctly. Okay, let's have you do the practice problems. So pause this for a second, try the practice, and then check back in with my answers. Okay, so first let's just check that we identified all the parts correctly. P is 5,000, R is 0.03, T is 1. When you're compounding annually, N is 1, quarterly 4, monthly 12. Okay, so plug that into the equations and you get. Okay, so you can check your answers now. For annually, it should be 5,150. For quarterly, 5,151.70 cents. Monthly, 5,152.08. Daily, 5,152.27. And continuously, 5,152.27 cents. All right, you ready for the homework?